Thank you, Trym. It's always a pleasure to have this joint webinars at Friday afternoons between Norwegian OpenAI Lab and Nora. And today we have the pleasure of having Robert Jenssen here. He's professor and head of the UiT, University of Tromsø Machine Learning Group. Robert is also an adjunct professor at the Norwegian Computing Center in Oslo and at the University of Copenhagen. He was also previously senior researcher at the Norwegian Center on E-Health Research. You had a lot of positions, Robert. I should also mention that Jenssen is the general chair of an annual conference in Tromsø, which is great. I've been there also myself, Northern Light Deep Learning Workshop or conference. I recommend this highly to the whole community. And not least, Robert Jenssen is also the leader of SFI Visual Intelligence, an AI Center for Research-Based Innovation in Tromsø. So today, his talk is titled Machine Learning and Visual Intelligence for Decision Support in Healthcare and Medical Image Analysis. So the screen is yours, Robert.
So let me just start by sharing my screen. So let me see, where did that presentation go? So let me just double check one tiny thing here, because something happened between the test and now.
Should also be mentioned that Robert is in the middle of a PhD defense, so he has taken some time off from that to have this talk today. So we appreciate that, Robert.
All right, so now I think I figured out what was happening. Let's see. Okay. Yeah, so I have all these workspaces on my Mac, and now suddenly class appeared in a different workspace than the presentation, and it got messed up a little bit. But hopefully now you can see a blue slide. Trym, can you nod if you can see it? Okay, so thanks so much, Claes and Trym. So it's a great pleasure to have this opportunity to give a talk. And I'm also very happy that the two organizations, Norwegian OpenAI Lab, Nora, has come together and organized these webinars and these presentations jointly. So that's great. So what I would like to talk to you a little bit about today is machine learning, of course, visual intelligence, basically AI for image analysis, that we conduct here at UiT in Tromsø together with lots of partners. So let's just jump straight into that. So the agenda for today, a brief background. First of all, I will tell you a little bit about our group here in Tromsø, about our research center, the SFI that Claes mentioned, and then we'll jump into the juicy stuff. So basically, I'll talk a little bit about utilizing, leveraging data from electronic health records and developing new machine learning algorithms to make sense of such data for the benefit of patients. Then I will jump into medical images and talk about innovative research that we have been conducting very, very recently on PET images to model the blood flow in the brain, basically. And then lastly, talk a little bit about some new research that we have been doing lately on interpretable AI, so deep learning. I will come back to all of these things, of course, as we move on. First of all, the machine learning group at UiT has been around for quite some time. So basically, since 2005, I would say, building stone by stone, step by step, growing a little by little, and quite a lot actually the last few years. So currently we're about 30, 35 people. We're faculty members, of course, but also several researchers, lots of postdocs, PhD students, master students. And what we do is machine learning research in the sense of contributing to the field of machine learning, the conferences, machine learning, computer vision, and so on, but also on the applied side. So you could say that the way that we operate is we develop new methodology, and when developing the new methodology, we very often have some application in mind. Could also be that we do not have some application in mind, but that the new methodology opens up opportunities to attack new applications. And then what often happens is that as we work on applications, we see that there's something missing on the methodology, the mathematics, the statistics, the physics maybe of the machine learning methods, and then we need to push hard on that part. So I'm not going to go into the details on these references you can see here. I'm just trying to indicate that we're very active, publishing, for instance, in pattern analysis and machine intelligence, neural networks learning systems, CVPR, ECCV, AAAI, and so on. So this is on the foundational research, but then, of course, applied in important domains in society, for instance, healthcare, which is the main topic on my talk today. We have a few months ago started the Center for Research-Based Innovation, which is called Visual Intelligence. So visual intelligence is attacking some foundational and really important research challenges in deep learning. So this has to do, for instance, with learning in a more efficient way from limited data. It has to do with quantifying uncertainty in our predictions, having robust systems, systems that are transparent in many ways, maybe know when not to operate, when not to give predictions, and also to be interpretable, such that users have a chance to understand why these predictive models come to certain conclusions or certain recommendations. And also to build a priori knowledge, for instance, physics of different problems into the algorithms to make them more efficient and better. So this is the key concept of visual intelligence. And the main source of information comes from various complex imagery data. So this could be medical images, it could be acoustic images from marine operations, could be satellite images from Earth observation, could also be energy type of images, for instance, seismic, or other types of sustainable energy imagery. So we have important partners from the Norwegian society, big companies, for instance, Equinor, Kongsberg Satellite Services, within healthcare in particular, General Electric, Vigmed Ultrasound from Norway, Cancer Registry. We have the University Hospital of North Norway, so basically where I am right now, and also Helse Nord IKT, which is the infrastructure provider for the North Norwegian health region. The research partners, well, that's UiT, which I am representing, and I'm also the director of visual intelligence as a whole, but also the University of Oslo and the Norwegian Computing Center. So this is a really, really nice consortium, I would say. So the vision, well, that's to drive forward deep learning for image analysis, attack these shared research challenges across a variety of fields in society. These fields cover medicine and health, the marine sciences, energy, and Earth observation, as I mentioned, but they are bounded together by the shared research challenges that I already mentioned. And the research challenges and these innovation areas in society come together in a grid where we hope to leverage and utilize synergies across. And you can find us on Twitter, Facebook, YouTube, and so on. And as Klaus mentioned, would be very, very happy if you would consider to join us for the Northern Lights Deep Learning Conference, which is organized annually in January here in Tromsø for the 5th time, actually now in 2022. Always with very good international speakers. Okay, so that's a little bit on the brief background. Healthcare, that's a really important domain in society that we are really focusing on quite a lot. So healthcare data analysis has been driving much of our research also in machine learning for at least 10 years. And one of the directions we have been pursuing quite aggressively is to try to identify patients at risk for certain diseases using data from electronic health records. I'll come back to what EHRs actually mean in this case. What I could say is that data from electronic health records are not recorded for predictive purposes to begin with, but more like routinely recorded data in the healthcare system at hospitals and so on, all across Norway and internationally. And Norway, at least at the University Hospital of North Norway, was very early internationally to record digitally this kind of data. What's important when you enter into this kind of research, which is interdisciplinary, is that you really need not only the technology people like us from the machine learning and AI side, but you really need the domain knowledge. And we have been lucky to have clinicians that more or less as a hobby, some 10 years ago, was really interested in AI and machine learning and tried to couple that into healthcare services on the path towards decision support. So these two has to come together basically in order for things to really have a chance to have impact. All right, so what is it that we have been focusing on? Well, I already mentioned it. So we've been focusing very much so far on the electronic health records and to leverage electronic health records for the benefit of patients and also the overall healthcare system. We're not alone basically to have such ideas, of course, but as I already mentioned, we have had access to data which has been relatively unique worldwide. So at some international centers, like at Stanford, for instance, they've all also been engaged in research like we have done, a little bit similar. And they have this really exciting Center for AI in Medicine and Imaging. And this red ellipse that you can see here in the middle of the slide, that's actually something I have put there to emphasize. I'll come back to why I did that a little bit later on. So it's about Stanford winning and really wanting to tell about this this best paper award they received a little bit of time ago. So electronic health records, that's basically routinely recorded data from the hospital system. So with us, every person, there's basically tons of codes associated with us in the healthcare system. Diagnosis codes, procedure codes, and it's a bunch of those things. We can think of that as data about patients. Could also be labels, actually, in certain problems that can utilize for supervised machine learning, but also text, and especially unstructured text. So for instance, nurses, they check on patients that are at the hospital 3 times a day normally, and they write a short report about these checkups. So that accumulates a lot of free text. Then you have blood samples, medical images, and all these kind of things. We've had access to data from the Department of Gastrointestinal Surgery at the University Hospital of North Norway for some 10 years. So as a part of a quality assurance project approved by the Data Protectorate at the hospital and all these kind of ethical bodies. And the main purpose has been to try to look for patterns in the data from the EHRs that says something about the risk for patients to have a certain adverse event. So something that we do not really want to happen after surgery. The target, of course, is to have intervention before something really bad happens. So this is just an example where you can see diagnosis codes and procedure codes for a certain patient. This is just to try to show you a little bit what this looks like. So you have certain type of codes for the main diagnosis and for the secondary diagnosis, for the procedure that the doctor initiated, and so on. This is an example of a nurse's note. So now you can see that the nurses, they fill out several points in a form, basically, free text, but it's sort of semi-structured because you have certain points that you need to fill out for every patient. But this accumulates data. So in our case, motivated by the clinicians, what we have been studying for the most part is to try to detect patients at risk for something called anastomosis leakage. So this is basically when you have a tumor in the intestine and the clinicians remove this tumor, stitch back together the intestines, and then unfortunately there's a risk of these stitches to break up. And then you have a problem. You have a leakage inside of the body. It can be lethal. We also studied and tried to detect patients at risk for infections in the wound, or to detect a state that is called postoperative delirium, basically a state of severe confusion on the part of the patient after surgery. So I could tell you a little bit about all of these things, but I will narrow it down to the last one. So of course, to be able to say something about this is important for patients, but also the overall healthcare system. And over the years, we've been working on many such problems, publishing on several different problem areas, wound infection and so on. But I will focus on postoperative delirium, one particular paper. So you can see that this is really interdisciplinary and funded by the EU, the Norwegian Research Council, Helse Nord, and so on, over many years. All right, so let's talk a little bit about postoperative delirium. So it's often defined as an acute confusional state after surgery. So especially if you have a major surgery, for instance, in the abdomen, then some patients enter into this very, very confused state, which is not good for the patient. It's also associated with increased risk of further complications, and also premature mortality, dementia, and so on. And a hypothesis from our collaborators at the hospital is basically that this state of confusion has been underreported in the Norwegian healthcare system. This is not good because then, first of all, you don't really know how big of a problem this might be. And it also has something to do with, of course, the patients. They are not then receiving a diagnosis they should have had, but also the reimbursement system of hospitals. So it's an important problem to study. However, the question, can we identify postoperative delirium from patient data from the electronic health record, is not easy to answer. It's quite complicated data to work with, and it's not necessarily such that we have off-the-shelf machine learning tools, algorithms, methodology, and so on that we can just use on this kind of data and expect good results. Actually, in our experience, this is quite challenging. So anyway, in close collaboration with clinicians, text, especially from nurses' notes, were identified as important to try to pick up on signals indicating postoperative delirium, but also other types of more like standard data from electronic health records, like the age, potentially the gender, and so on, from the patients. However, there's a problem. So we don't really have annotations. So we don't really know which patients that might have had delirium or not in the past. And especially if the hypothesis of this being an underreported problem is true, then we can't just go to some diagnosis code for postoperative delirium and say that, okay, we have labels here. Let's just try to train a machine learning system such that we can predict on future patients whether they will develop postoperative delirium or not. So we are really in a non-standard situation when it comes to machine learning, where supervised machine learning is difficult. So we have to do something else. So as an example of this kind of research, what we ended up doing was to think a little bit out of the box, maybe, and introduce something we call clinical anchors. Of course, not entirely just out of our own heads. We're also building on some research by some other groups, especially actually at Stanford and at New York University. But anyway, we took this kind of framework of clinical anchors quite a long way forward. So what is a clinical anchor, and why would we want to define clinical anchors? So recall, we don't really have labels for our problem, whether a patient had postoperative delirium or not. But a clinical anchor is such that if we have an observation that with more or less 100% certainty indicates the diagnosis, then we call this a clinical anchor. And the idea is to exploit this information. So one example could be the strep test, so halsbetennelse in Norwegian. So if you take a strep test, like on this baby, and it comes out positive, then you almost for sure have an infection, so halsbetennelse in Norwegian. However, if the strep test is not positive, then we can't really conclude that strongly. You can't really say whether you have infection or not. The point is that if the test is positive, it's a really strong indicator for a positive case in the sense of having this kind of infection. So this is just one example. Now, we have a different problem. We have postoperative delirium. And the idea, motivated to a large degree from our clinicians, is to look for such anchors in the nurse's notes, the unstructured text from the nurse's notes, that would really indicate that a patient actually had postoperative delirium if we could find such an anchor. But recall, if we don't find an anchor, then we don't really know for sure whether we had postoperative delirium or not. So it's a new way of thinking. In any case, it's not obvious what such clinical anchors for postoperative delirium should be, how to find such anchors. Let's come a little bit back to that in a few seconds. But let's say that we can find such clinical anchors for postoperative delirium. What then? So this is the idea. Let's say that by some method, we were able to identify very, very strong indicators in the free text from the nurse's notes that indicates postoperative delirium for certain patients. So let's say that we color those patients where we found the anchor. And then the black ones here, they are patients where we did not find the anchor. Then we have a bunch of data from the electronic health record. So this could be from the remaining part of the free text, where we do maybe some NLP. The most simple would be bag of words analysis. It could be traditional data like blood sample, gender, age, and so on. It could be other kind of features that we basically engineer from the electronic health records. In our case, actually, we have more than 20,000 numbers when you do it like this to represent each patient. And the idea now is to use machine learning to find the patterns in the data that indicate whether patients have the anchor or not. So not the true label, but the anchor. And we use machine learning and AI also for that. I'll come back to that a little bit later. But let's now say that we could find these clinical anchors in our problem of postoperative delirium. So then we want to find these patterns that indicates the patterns in the data for anchor or not anchor. Well, actually, in our case, in this part, we train a very, very simple and straightforward classifier based on logistic regression. So nothing super advanced here. There are many good things about logistic regression, easy to interpret, easy to understand what's going on, which weights that are important for different features for this problem of distinguishing between anchor or not for postoperative delirium. So in our case, we found this to be good enough. And then, if we can do this now, train a classifier, look for patterns, anchor, not anchor, what then? So let's say we have this trained model. So then in the operational phase, this is how it works. So we have a new patient coming in. We've never seen this before. And we ask, so if we go to the nurse's notes, I haven't explained actually how we define anchors, but we have a way. So let's go there and look. Do we have an anchor, clinical anchor, for this particular patient? Well, if you find such an anchor, then it's sort of easy in this case. Then we just say that this patient has postoperative delirium, or basically will develop postoperative delirium is a more correct way to say it. But what if not? Well, recall, then I said that you can't really judge something on the basis of not finding the anchor. We have to look into the patterns in the data then. And we already trained our classifier to distinguish the patterns of electronic health records data with respect to anchor or not. So then actually we use our classifier. If we find a pattern in the data that indicates that, that we could have had an anchor in this patient data, then we predict, yes, this patient had postoperative delirium if we look retrospectively, or this patient will develop postoperative delirium if we look prospectively into the future. And if we do not find patterns for clinical anchors in the data, well, then we predict not postoperative delirium for this patient. So that's how it works. And this was what we've done in our work. Then you might ask, so what about these anchors? I'm not going to go too much into this because of time. If you're interested, you can have a look in our paper. What I could say is that it's based on clustering. So basically we take text, free text from the nurse's notes. We do the simplest of NLP that you can think of, the bag of words. We cluster the data, and we have an interactive approach where clinicians study the clusters and look for groups of words in the clusters that they believe are good anchors for postoperative delirium. So there's also a novel aspect here, but I won't really go into the details. In the end, based on this analysis, clinicians suggested 3 different types of anchors for postoperative delirium. One very simple, let's say that the word confused is appearing in the nurse's notes about the patient. That could be an anchor. A little bit stronger anchor is if the word confused and the word disoriented appears. And the third one, confused, disoriented, and unclear. So 3 different types of anchors, all based on this clustering and interactive approach with the clinicians. So then basically with these anchors, we then trained our classifier to look for these patterns to indicate such anchors. And then we had a clinician, or actually several clinicians, manually browse through hundreds of journals for patients to create, in the test time, of course, basically annotations for postoperative delirium or not for these patients to check whether our predictive system matched what the clinicians thought would be a correct diagnosis when really doing this manual work of looking into all these journals. And what we could say is that really promising results from this new way of thinking for our clinicians, very interesting because it seemed to corroborate their hypothesis that this problem is underreported, and that could have a big impact both for patients and also the overall system. So this was a really, really satisfying interdisciplinary work where clinicians motivated the study. We needed to do new stuff on the machine learning side. We needed to develop methods that didn't exist from before. And then we needed to have this interactive approach where we went together and then worked and published. And to our big, maybe surprised, at the same time as Stanford won their Best Paper Award, we won the other Best Paper Award in the same category, basically, with our work in the similar fashion as Stanford and their center. So this just shows that we in Norway, and of course not only us here at UiT, but elsewhere in Norway too, there's no reason to think that we lag behind the international groups. We can do really good work also from our point of view. So this was an example of work where we basically try to leverage data from electronic health records. And this is just one example of work in that direction. I would also like to mention medical images, because this is something we have also focused quite a lot on, and which is, as I mentioned, very important for the Center for Research-Based Innovation, visual intelligence. So let me tell you a little bit about some work that we've been pursuing in this center, and also in very close collaboration, of course, with users, so basically clinicians. So now the problem is to try to model the blood flow in the brain for persons. And this is, of course, very important to say something about their health, their clinical status, and it's very much used. And today you have PET imaging systems where if you combine the PET imaging with extracting blood from the arteries, you have a way to model the blood flow in the brain in that way. It's called a compartment model. However, the problem is that you need to extract blood physically from the patient at the same time as you do the PET imaging. Now, this has some problems. So first of all, it can be very unpleasant for the patient because you have to basically physically extract, as you can see, tubing. You have to extract blood from the artery of the patient. And there are lots of practical problems with this. And there are some alternatives where people have tried to basically model blood flow in the brain without extracting blood physically like this, but very little work has been done on this. So the main aim here is to be able to, based on PET imaging, but without extracting blood physically like this, be able to model blood flow in the brain and then spare the patients for unpleasant experience. It's also much, how to say it, it could save time and many other aspects and be a real innovation. So this is a very recently published work by Samuel here. He's actually defending this work today. So I'm prioritizing, of course, to give this presentation to you. And then I'll skipping a little bit of the defense of my student, but I'll be back for the end of the session. He's doing very, very well. And in collaboration with Uppsala University Hospital. So here we had data from a certain number of patients, 25 actually. In this context is quite a lot. Of course, ideally it would be much more, but in this context it's quite a lot actually. So how does this work? So the novel part here is to try to extract features from the PET images. So features that we can use in a supervised machine learning system where we have access to the true blood curves for some patients, and then to train a prediction system that, based on features extracted from PET images from each patient, will predict the blood curve that you would get from extracting physically blood from the arm of a patient. So it's supervised, So we do have extracted the blood curves for these patients in the training set. But of course, the idea is to have new patients coming in operationally at the hospital and then not having to extract blood from the arm and still be able to predict a good blood curve. So the blood curve that says something about the uptake of this radioactive substance basically in the brain as you undergo PET imaging, which again is used to model blood flow in the brain. So there's a whole process now, lots of work that we did to be able to extract features from the PET images. So we had to identify regions that are related to certain blood veins in the brain. We had to basically try to extract information about the flow through some pixels in these images as we perform the PET. And in the end, what we get is certain curves. So these curves basically that are now related to certain regions of pixels in the PET images. And these curves, which are then our features, are used to predict the true blood curves that you would obtain by taking blood physically out of the arm of the patient while performing PET. So in the end, this would then be the setup. So we have our patients. We do this feature extraction. There's a novel part there that I don't have time to go into. Then we have a machine learning model. And then you could ask, okay, what kind of machine learning model? So there you have many options, but I'll come back to what we actually used in our case. And the idea is to predict the true blood curve, right? We have access to the true blood curve for some patients in the training set. And then, as always in machine learning, we have a loss. We measure the loss, and we update the machine learning model as we always do in such kind of setups to minimize the loss. And this actually turned out to work quite well. So what we in the end opted for when it comes to the actual machine learning model is two different things. So one is Gaussian processes. So maybe you've heard about Gaussian processes. It's a Bayesian model, but you have a certain way to model the covariance structure of your features. So basically a kernel method, if you heard about that. Important thing is it gives you a prediction. It also gives a certain uncertainty estimate of your prediction through this Bayesian way of thinking. But we also trained neural networks, so LSTMs, long short-term memory neural networks, because our features develop over time. So we basically have a time-varying signal that we try to predict. So this is within the realm of LSTMs. In the end, by having a training set, a validation set, test set, the usual setup, both of these approaches actually work quite well. We have limited amount of training data in our case, not so many patients, and then standard machine learning methods like Gaussian processes could have an edge. And actually we opted for Gaussian processes in the end as the kind of main machinery. So anyway, standard setup turned out that based on Gaussian processes, based on this feature engineering from the PET images, we could predict with high accuracy the true arterial input function, which is the name of this blood function I talked about that you need to extract physically from the artery in the arm. So what this means is that if you have a system like this, where we don't need to invoke this unpleasant and not very practical method of extracting blood physically from patients, then, and still being able to model the blood flow in their brain by Gaussian processes, machine learning, predicting these functions, then there's a really, really benefit and quite a high chance of actually innovating the hospital system to actually have this kind of method used in practice. So this is the next step, of course, that we are working on. All right, so now I told you about two different directions, AI for healthcare. So one based on electronic health records in general, new machine learning methodology development. We really have to tackle this problem not having labels. We have to work in different ways, anchors, semi-supervised, unsupervised, and so on are directions we are really following. Then we moved into medical images, and here the issue was to extract and exploit PET images. And I should really say that PET is really on the rise as an imaging technique within medicine and health. There's always new developments on the imaging systems. And here in Tromsø, we have a brand new PET center. So we have a lot of interaction with the PET center and lots of problems we're working on. But what I talked about there wasn't really very innovative on the machine learning part itself. There we basically leveraged Gaussian processes without really changing the machine learning method itself very much. But also in lots of other directions when it comes to medical images, it's all about deep learning. So all about very, very big artificial neural networks to do the predictions. So that's especially when you work on the raw data, the images themselves, and not through some kind of feature engineering like we did with this PET example I just showed you on the blood flow in the brain. So I could show you several examples in this direction, but I will limit myself to some new kind of methodology research we have been pursuing lately when it comes to interpretable deep learning or interpretable AI. So there's a lot of attention right now to this issue of trying to have ways to explain or let the user understand the reasons why a predictive system, for instance, a deep learning system, makes the prediction it makes based on the input it receives here and now. So this is, of course, to try to open what's often referred to as a black box. So mathematically speaking, neural networks are not really black boxes. So in terms of geometry and the mathematics behind, at every step, you can understand what's going on. That's not a problem. But when you combine all these convolutions that you have in convolutional neural networks, all the layers of processing, all the nonlinearities by ReLU nonlinearities and so on, in the end, especially for a user which is not familiar with machine learning and AI, it can be difficult to understand basically why this system predicted what it predicted. And it would be useful if the system can try to explain itself. So especially by providing kind of a heat map of the input that is being processed right now, and to say that, okay, these are the important parts in this image, for instance, that is driving my prediction. And there are many examples of deep learning systems being fooled. For instance, this example where you've trained your system on a bunch of categories, recognized different categories. Turns out that the system is maybe not really focusing on pixels, where you sort of know that the horse is in this image, even though it classifies the image as a horse. It actually picked up on this text, basically the name of the photographer that took photos of horses, and those photos were part of the training set in this case, such that actually when predicting horses, it's actually by picking up on this text. So that's of course not so good when you transfer your trained model. You have images that are of horses and do not have this text of the name of the photographer, and then the system may collapse. So it's really important to move into interpretability and AI. So this problem we are working on. There are other examples where the system was fooled by medical images having sort of inserted this kind of metal token inside of the body that the system picked up on. So data from a certain hospital had this token, such that if you transfer the model to data from a different hospital, different instruments, then the system would just be totally confused. So that's why it's important to run this kind of post hoc analysis to try to check that your system, deep learning system, has really learned useful knowledge, such that you can trust the system, transfer it to new situations, and so on. So this is ongoing research by many groups and also by us. I will tell you a little bit about recent work that we did. And the idea is to not only try to say something about which pixels that the system focused on that are important for the system, the deep learning system, when making a particular prediction, for instance, say that this is a cat, but also to actually say something about the uncertainty of the importance quantified by the system on a pixel level in such systems. And this is a little bit new. So this we just published in the journal Medical Image Analysis very recently. And we did this in the context of polyp segmentation, colorectal polyps. Could have been in different contexts, but we had data available for this particular kind of problem. So these polyps can develop into tumors. So it's important to detect them. And this is basically a segmentation problem. Image analysis, segmentation. And we want to say something about the uncertainty when we have a system trying to explain itself. So give importance to certain pixels, say these are the important ones, but can we quantify the uncertainty in this quantification of importance on a pixel level when making predictions? So we then came up with something we called Monte Carlo guided backpropagation. So it builds on a method called guided backpropagation. So guided backpropagation is one of the most used and well-known and really influential methods to try to quantify importance, give interpretability into a deep learning system. So you have your input. So now you've trained your system, you have some input, and you predict something. And then you want to provide a map where you say that the system explains itself. This is what you can see on the right-hand side. And it says that these are the important pixels or groups of pixels for my prediction of a polyp at this particular location. And then you can see that we have pixels in this system sort of surrounding what a clinician can see to be the polyp, but also some pixels that are not very near the polyp in this space. All right, so what did we do here? So we leveraged something called Dropout. So Dropout is ubiquitous in deep learning. It's very, very simple. It's surprisingly simple. And it's one of those things you just, why didn't I come up with this? So basically, when you train your deep learning system, when you do your epochs of training, you shut down neurons randomly over each iteration of this phase. So for instance, half the neurons. So this means that radians are not flowing when you shut down neurons. Basically means that you insert kind of a randomness into the system. And when you train a system with Dropout, you regularize the system, and you can also go back into your iterations and basically kind of pick tons of different networks then that could provide like an ensemble that we use in the prediction phase. And we exploited this in a new way, very, very simple way, but in a new way. So basically what we did was we utilized Dropout. That you can think that when using Dropout, you actually create a big ensemble, different deep learning prediction methods. Then basically what we did was we let each of these systems that come out from the Dropout procedure explain themselves And then we quantified uncertainty in a very, very straightforward way across these explanations. So now you can see that if you only use guided backpropagation on the left-hand side, you can see that all these pixels are kind of quantified to be equally important. But when you use our method in addition, then you see that, okay, all these pixels are quantified to be important, but we are more uncertain about those pixels that are colored red. So that's based on our extension of guided backpropagation. And the green pixels, well, they are the most sort of confident, important pixels. So it's quite simple method. And this is also why I think that maybe other people will pick up on this. We've already seen that happening, and maybe be developed in a better fashion by other people, by ourselves later on. So the key point is not only to say something about the importance of pixels driving certain predictions, but also to quantify the uncertainty of this importance when we have interpretable systems like this. So with that, I'm concluding this talk for now. So hopefully I was able to show you some directions of research in healthcare and AI. Of course, focus on the work that we are conducting at the UiT Machine Learning Group and at the big SFI Visual Intelligence with lots of partners, and also UIO and the Norwegian Computing Center. So I would say that there are really exciting times ahead for machine learning and visual intelligence, which is what I refer to when I'm talking about machine learning, deep learning for images within the health domain. And we need both people from the technology side, of course, but we really need domain experts come together in interdisciplinary work. We also need the surrounding part to be considered, the ethics, the law of new health technology. All these things come together and provide really exciting avenues for research, and also together with data, trust in the Norwegian society between people, researchers, governments, data providers, and so on. There's no reason why we in Norway should not take the lead internationally. I think we're already in good position, but take a even further strong position in this type of research, innovation, and implementation eventually of machine learning systems in health. So with that, I would like to thank you all for taking the time to listen to this. Of course, there are some people I should thank, and you can see the names here. Thank you.
Thank you so much, Hubert, for an extremely interesting talk. And I agree so much. I mean, AI in health should be a topic that Norway is well fitted to do well. We have so many great groups within this topic and so much good data. So this is interesting. We only have a couple of minutes for questions, so I will just go fast through a couple of questions we received. Let's see, one question from Mohibullah. Can the attention-based deep learning models help in interpretability?
Yeah, so that's a really good question. So I think the short answer is yes, basically. So attention, so for instance, if you have, let's say, different sources of image data, for instance, already there you can have good use for attention in interpretability to sort of see which kind of modalities that are highlighted, and also attention on a pixel level.
And also I have to mention, as you said, Dropout is one of those inventions that why didn't we do it? But the same maybe applies to the method you mentioned that you have actually made for quantifying the uncertainty about, because if I understood it correctly, you then quantify the variability between different dropout instances, right? So you have, is that
exactly, yes. Yeah. Yeah. So you basically just take something which is already there, and compute a couple of numbers.
Exactly. So this is very interesting. I think that's also one very clear idea that could be. Have you kind of pushed this further? I guess this is a topic of research right now. What's kind of the way to go within this topic? Could this be utilized in other kind of? Could you utilize this idea in other settings as well, or build up on it?
Yeah, so that's a very good, good. Not to. I should be maybe careful to get too excited, but in a different context, when we work with these postoperative adverse events, actually, and we try to say something about the risk of blood infections, and we work with blood sample data. So now we have time series data. And so now we're working a little bit differently, with different kind of neural networks. And there the interpretability comes from something called class activation mappings. So it's a little bit different from guided back propagation, but there we also basically did relatively similar kind of thing. Insert dropout into the class activation mappings, create these different ensembles. We just published this in the Journal of Biomedical and Health Informatics, and it seems to end up on the cover of this journal issue. And it's basically sort of the same idea, just transfer to different data and a little bit different interpretability method.
Because as you said, this helps maybe also the clinicians when they do decisions to understand things, but this is also the way most people do decisions. It's not only kind of looking for the optimal solution, it's also kind of the risk or the variability or the chance or whatever. So this kind of quantify this. So I guess this is a very good tool, not only for humans to kind of understand things, but maybe also for building upon future kind of algorithms to expand them. We have one more question here. No, that was only a quick question about the link to the paper you showed. I guess that was the best paper award that you received. If you have the link, Robert, it would be nice. We could maybe post it in the chat.
I can post it. Yes.
And it's already 3 o'clock, so I think with that we will end the session and say thank you so much to you, Robert. Trym, I don't know if you have any final words today.
Thank you, Robert, for his talk, and wish him good luck with his student this afternoon. Hope the PhD defense goes well.
I hope the same. I think the same. I think it goes well. Thanks a lot.
I'm sure.
Thank you.
Thank you so much. Thank you, everyone. And have a nice weekend. Put on your nice weekend clothes and celebrate the good weather, at least here in the south. Bye.
Bye-bye.